So hello and welcome. We're happy you could join us today, and I do hope you're having an exceptional day. I'm your host, Charles Collegy, the security analyst for Accelerated Strategies Group. Today's Security Boulevard webinar is brought to you by ARMO. Today I have with me the CTO and co-founder of ARMO, Leonid Sandler, and he'll be speaking on how safe is your secret. Leonid, if you could just please introduce yourself to the audience.
Hi, everybody. Thank you for joining us today. My name is Leonid Sandler, and I'm the CTO and co-founder of ARMO. My history goes way back to software security. I've started as a designer and developer of video DRM solution, which was used by the biggest service providers platforms in the world. And part of that work was to understand how software security systems gets attacked and what motivates the attackers, how they operate, what tools they use, etc. And a couple of years ago, me and my team decided to take this and bring it to the cloud so that we can basically secure data and services in the cloud.
Thank you, Leonid. And as you can see, he is really eager to tell you everything you need to know when you're looking at choosing a Kubernetes secret management method. However, Leonid, you're going to have to wait just a few more minutes as I need to take care of some housekeeping items. The first thing everyone needs to understand is that this webinar is being recorded. So later today, it will be available for on-demand viewing. So you will receive an email with the link, but at any time you can go to securityboulevard.com and gain access to all of the archived on-demand webinars, this one and everything else that is there. So feel free to take a look at all of the other webinars we have available and tell your friends about this one. So now I'm going to take just a few minutes to talk about our Big Marker platform. So on the right side of the screen, you'll see a chat button. This feature allows everyone online to contact us, to reach out and create a dialogue amongst ourselves and amongst the rest of the audience and participants. And we really encourage your feedback. We want to hear from you. Now, for questions, don't use the chat, but we have a Q&A tab, which is directly to the right of the chat. So that is the one we wish you would put in any questions. And we'll try to answer as many of you submitted questions as possible before the end of today's session. But should we not be able to get to everything, I'm sure ARMO will follow up with you. Now, at the end of today's webinar, we will be awarding 4 $25 Amazon gift cards. So please stay with us and see if you have been selected. So now it's time to jump into today's session. So Leonid, the time is now yours.
Thank you. So let's start. We're going to talk about secret management, secret distribution in the Kubernetes platform and in cloud native in general. We'll talk about something about secrets and different ways of secret management, etc. So I won't read the agenda and we can just jump right to it. First thing I want to say is that I can't possibly know every single feature and every single product and the differences between them. So I'll try to focus on the fundamentals and the most common and most serious parts that you need to know when you go and design the solution for management of your secrets, or if you assess the existing solution and see how safe you are. So the first thing is what is secret, and obviously you already know what the secrets are and why they are dangerous. They guard our most important assets, information of our customers, information of our own, and obviously we want to keep them safe. Secrets are used in multiple security operations like signing and encryption. And we have to be very careful when you say we protect by encrypting. The protection and encryption is not the same thing. Encryption is a function. Everyone can use it. Encryption becomes a protection only if you know how to keep the secret safe, how to separate the lock from the key, and make sure it's not leaking out. And eventually, although you do have to bring the lock and the key and to open the door. So the question is how you do this and how you make sure that only the right lock gets the right key, only the right application that's supposed to get that key will get it. Okay, and this is where authentication comes in, because authentication allows one party to authenticate the other. I want to know who am I giving the secret to. I need to know who you are. And again, let us not confuse here, authentication is not the same as identification. You say who you are, and that's not enough. I need to make sure that you are who you say you are. And for that, usually people use secrets. So how can I authenticate somebody who came to me to get the secret if he doesn't have any secrets? So we call this like a chicken and egg problem, or problem that is called a secret zero. Okay, and when we talk about authentication, also there are different levels of it. We all know about passwords, and we all know about passwords are not safe. So the cryptography teaches us to use at least three different levels of authentication. Authentication is based on something that you know, which is usually a password. Something that you have could be, if you all remember this old RSA tokens to connect to VPN of the company, or could be a second factor authentication using your mobile device or something else. And a third one, which is the more like a biometric type of authentication, which is based on something that you are. However, if we bring this to the cloud environment, then we have a problem, because there is nobody there sitting and typing password on the keyboard. So everything that we know and everything that we have is exactly the same thing. How can we distinguish that? Is this really two different levels? And let's agree that if I have two things, or I know two things, it doesn't really empower the authentication principle. It's still something that I know or something that I have. And something that you are is something that we'll talk about at the end of this presentation. So sometimes you ask people, how do they protect their secrets? How do they keep them secure? And they say, well, we will encrypt them. And I will say, okay, encrypt with what? Oh, we have a key encryption key and data encryption key and multiple layers. Fine, you can name them any way you want, but naming them doesn't make them any more secure. The question is how really secure they are, who can have access to them, and who can abuse access to them, which is probably the more important question. If we look at the life cycle of a secret, which is a very important thing to look at, because in most cases, the life cycle doesn't start when the secret gets loaded to key management. It actually starts the way before. The secret gets created, and the moment you created it, you don't want to lose it, so you want to back it up. When you back it up, you start using it in some scripts, because we all use infrastructure as a service. We know what the Helm charts are, what the YAML files are, etc. And we put our secrets into those files, and then we back up those files. So we also need to make sure that those files are secure. Eventually, we load them to a key management system, whichever type. We'll cover a few of them today. Okay, we have to define the permissions. And from that moment, there are two different modes of work. One of them, the legacy one, or the older one, is the pull mode, where application comes and asks for the secret. And in order to do this, application needs to present something, or to pass through what somebody call authentication. I would call it identification at this stage. And application would get a secret. And the other mode is the push mode, is where the orchestration environment actually pushes the secret to a file or environment variable that this application will eventually have access to. And the application will just read the file. And this is the life cycle. We'll keep it in mind when we talk about the security of different stages. The two fundamental problems that I do want to cover today and want to focus your attention on are, first one is, how do you keep your secrets safe at rest? They are somewhere in the key management system. They're stored somewhere. They're always there, probably even backed up, etc. We can go in more details and figure out how these backups are secure. Okay, but let's stay at the key management system for now. We need to figure out how we store those secrets. If they are encrypted, then encrypted with what? If they are not encrypted, then how they are protected. Okay, and the second part is, who is asking for them? Do we really know which application came to us and asked to get the secret? Especially because when application comes and say, I need a secret, we don't know whether we really talk to this particular application or somebody just took a access token or identity token and passing it on behalf of that application or just for its own. So the other thing to keep in mind when we discuss the security of our key management solution is what attackers do. How do they get to our system? Nobody can stick a finger in the cloud and scrub a few bytes. So it's always about software. And we look at the different methodologies of risk assessment or security posture assessment. Could be Lockheed Martin kill chain or Mitra attack. I've tried to condense this to three major points. They're all more or less agree on them. Sometimes they describe them in more details and more granular boxes, but in general, it comes down to misconfiguration, credential abuse, or software vulnerability exploits. These are three major attack vectors or insertion vectors for initial access to our system, and most of the attacks use one of them. And when that happens, what those attackers can do? As I said before, it's always about software. They will need to insert their malicious software to do something bad to our system. Of course, they can use the existing software in an appropriate way. For example, if you left your S3 bucket open, they can just go to S3 and download everything. There's no need to change anything. But that's the simplest way. Let's say that we pass that point and we actually do protect everything that we need in the infrastructure. So the malicious actors will need to insert their software, and they can do it either by changing the behavior of existing software or by corrupting or adding more software to our system. These are the attack vectors. So when we look at the protection of our key or protection of our architecture, we need to see this through the eyes of the attacker rather than through the eyes of the software developer who says, I'm doing 1, 2, 3, 4. It doesn't matter. What matters is what bad actors can do to abuse what software developer does. So the first type of key management system we are going to discuss today is the cloud key management system. Of course, every cloud vendor has their own implementation, so I'll try to stay in kind of a common denominator between most of them. And as I said, the two major issues that we are going to look at is how do you store the secrets and how you deliver them to the application. So when it comes to cloud KMS, there's practically nothing we can contribute or nothing we can help cloud vendors to protect their system at rest. They have all the technology, they have all the knowledge, they have all the tools, they have people on watch 24/7. They can do a superb job protecting their storage. I don't even want to go there and try to figure out what can be done wrong. So for this particular use case, let's go left. Let's shift left and see what happens between the applications and the cloud KMS. When application talks to cloud KMS, it may use two different types of interfaces. Usually it's a REST API, kind of more legacy type of interface, which is also specific. There's no generic way to do REST API. Most of the cloud vendors don't support a standardized KMIP. So the REST API is also proprietary, but application comes to the cloud KMS, presents some sort of a token and says, please give me the key. Again, in this scenario doesn't have any authentication in there because that token not in any way bound to that application. That token would be parsed by the key management system. Key management system will identify what keys application is asking for, check some permissions, and basically take this key from the storage and deliver it back to the application. The other way is IAM, which is Identity and Access Management integration with the cloud vendors, which usually integrated on the cloud vendor level is integrated with the VMs. So everyone who runs on the VM can access metadata service, get IAM token, and use that IAM token to authenticate to the cloud KMS. Now, most people don't know how that mechanism works, but under the hood, that information is basically a token with some secret key, and the SDK provided by the cloud vendor to practically any languages we develop our application in will use that key to sign the request and send it to the KMS. So there is some kind of a signing in here. It may imply authentication. However, any software that runs on that machine can do this transaction. So there's no really real knowledge about what application on that particular node is asking for the key. All you know, they are probably running on that particular node. However, we've done some experiment. We took this IAM data blob from the metadata service. We took it out of the machine and went to the KMS, and we received exactly the same key. And then we became even more bold, and we took it out of the cloud and tried to use it from the machine at home, and we still received the same key. Of course, connectivity is required, okay, there's no question about it. But as far as security is concerned, this IAM token can be copied and used just like the REST API token. There's no real authentication in there. There is some protocol, there is some function to be called, but any application can basically use that and obtain necessary secret materials from the key management system. Cloud vendors can do a better job, or maybe they will. They could probably integrate the IAM with their own instance of the Kubernetes, their own distribution of the Kubernetes. And they can even try to identify which Kubernetes pod is asking for the particular IAM message and change it per pod. Still, remember the intrusion ways. If I manage to inject my own software, if I'm able to use a stolen credentials and create my own pod, I can map any key. I can basically ask a Kubernetes to map any key to my pod, and I'll still be able to get that key from the key management system. So the lack of authentication is the problem here. And it's not really a big surprise, because applications store keys in the key management system because they don't want to have them on them. They don't want to have anything hard-coded. So how can I authenticate something? How can I ask for something secret if I don't have any secret? Again, this is back to the secret zero, this chicken and egg problem, because in order to authenticate, you need to have something. Okay. The next one is Hashicorp Vault, which is probably the most popular cloud-independent key management system. It has a lot of features. It's used practically everywhere. Okay, and I want to again to look at this from the same perspective that we've looked at Cloud KMS, how the secrets are stored and how applications are authenticated. I assume that if somebody can solve these two problems, that could be a perfect key management system. So in Vault, actually there is a problem, because it's open source component. You can deploy it on your own. You can map a persistent storage volume to it, but now you actually need to protect that volume. How you do this? The Vault has no secrets. It comes from public repository. Everybody gets the same Vault. So if you look at the instructions, or you can look at the recommendations on their site, you'll see that the most popular method of getting secret zero to Vault is to use Kubernetes secrets. Well, as far as chain of trust is concerned, if Vault is dependent on Kubernetes secrets, then I would ask myself the question, why would I use another leg? Why would I use Vault if I still securely dependent on the protection that is done by Kubernetes secrets? Now, Vault can do better, okay? So I'm not saying that Kubernetes secrets is the only way. Vault can do a cloud KMS as well, or even cloud HSM. But then we go back to the previous slide. If Vault is a client of the cloud KMS, then the same problem we discussed before comes back. How cloud KMS knows that it delivers the secrets to Vault? Because initially, Vault doesn't have any secrets of its own. Okay, so the problem of secret zero is going to keep hunting us. It's not solved here. Making another level and another level doesn't solve the problem. It just makes it more complicated, more difficult to maintain, and of course, if something happened, more difficult to figure out what happened. But now let's look at the left-hand side. The Vault is a little bit more flexible. It has two types of APIs, maybe even more. As I said before, I don't know all of them, okay? But these two definitely exist. Application can call a REST API in Vault and ask for a key. And that is done exactly the same as in the cloud KMS. Application presents a token which it received from administrator of the system. The Vault would open the token, see what key application is asking for, and deliver that key, assuming that this key, of course, exists in the database. Now, Vault is nicer in certain sense because it also supports the interface that's called KMIP, which is a key management interoperability protocol. It's kind of a little bit older, but it was very popular before cloud KMSs. It was done so that popular software packages like databases and web servers would be able to work with different key management systems because all of them need secrets. So the KMIP was there before, and Vault is still supporting it. The other interesting field Vault is doing is supporting the push mode, which I explained earlier, which basically pushes the keys to the pod. It has some sort of integration or some sort of interoperability with Kubernetes by injecting a sidecar into the pod. And that sidecar, which is, by the way, the same sidecar for any pod that Vault is running or the system is running, that sidecar authenticates to Vault. Again, we ask the same question, authenticates with what? Every pod gets the same card, same sidecar. So, and there is no initial secret. So the word is, or the explanation that the sidecar authenticates to Vault is kind of a faulty. There's no real authentication in there. More of identification, as I mentioned before, because this sidecar will basically take either YAML or name of the pod and then go back to the system and see what secrets are mapped to that pod, and those secrets will be delivered to the application. And Vault will push them, and application will open a file or environment variable and just use them. So I'll leave it to your own judgment to see whether this solves the problem or not. Okay, in my view, it's not really solving it. The next is the Kubernetes Secrets. The Kubernetes Secrets is a native solution, is a native implementation of Kubernetes, which is working the following way. The secrets are delivered to Kubernetes API using either kubectl or some other APIs or service account like Tiller Point of Helm, etc. And then they're stored in the etcd database. This database could be either clear or could be encrypted, but if you read the instructions on Kubernetes side, they'll tell you that even if it's encrypted, it's not such a big security advantage because the encryption key is stored on the config file, which sits just right next to the etcd itself. So if it's encrypted, it basically covers everything, but there's no really specific encryption for the secrets. etcd, if Kubernetes is configured properly, it would only talk to the REST API, to the kube API. So there's like mutual TLS authentication between them. And if somebody tries to talk to etcd from outside, most likely, again, if it's properly configured, nobody will be able to do it. So secrets are stored in the object called Kubernetes secret. And the question comes up is, what's the difference between Kubernetes secrets and config maps, which are also stored in the same place and managed in the same way? And why one of them is called secret and the other one is not? So clearly, there is no technical distinction between the secrets and the config maps. They're handled in exactly the same way. However, Kubernetes designers thought that it would be appropriate or would be even useful to separate between these two objects so that the administrators of the system could provide different access rights, different RBAC rights to these two objects. For example, you can give access to secrets to a certain amount of security related people, while the config map would be open to a broader group of developers, DevOps, etc. And this is why Kubernetes called them Kubernetes secrets. However, as I said, from the technology point of view, there is no difference between the secret and the config map. However, most of the DevOps people that I've talked to, they say that the Kubernetes secrets is the most convenient way for them to work. This is the way they manage their entire environment. This is the way they configure their components, their scalability, their deployment models, etc. So from a convenience perspective, the Kubernetes secrets is the most appropriate way for them to work. And the reason they kind of hesitate is because they can constantly hearing from other security vendors or security solution vendors, cloud vendors, that Kubernetes secrets are not secure because they are stored unencrypted in etcd. There is a joke going around that because they are stored as base64, base64 is not encryption. Indeed, base64 is not encryption, but etcd in most cases is managed by the same cloud vendor as the key management system of the cloud vendor. So if cloud vendor wanted to do a good job protecting it, they would have done it. Okay, there's no reason for them to be able to protect persistent storage of the KMS and not to protect persistent storage of etcd. As I said before, on the TLS level and the Kubernetes configuration level, the etcd would only talk to kube API. So there's no problem with communicating with this from the interface perspective. The only reason why we discuss encrypted or not encrypted keys at rest is because somebody thinks that you can get access to the persistent storage of etcd database. And from that standpoint, I think that cloud vendors can do a very good job to protect it, so we won't have to worry about this. And then the question will go back to how applications are identified, or how the applications are authenticated to actually deliver them appropriate keys. Now, what happened when the workload starts is the kube API reads the YAML file, the definition of that workload, and see what secrets the workload developer or DevOps engineer has asked to map to this secret. The kube API would communicate with the kubelet, and there is a 100% trust between the two. Kubelet is absolutely trusted. It can ask kube API for anything and get anything. There's no special authentication in terms of capability of kubelet. There's authentication between the kubelet and kube API in a sense that kube API knows that it talks to kubelet, but not what one kubelet can or cannot do. And therefore, a kubelet receives the secret from the YAML file and pushes it either to a file or to environment variable of the application running inside the pod. And this push mode, the secrets are basically propagated automatically. Application may need or may not need that secret, but if YAML file was asking for it, the secret will be pushed to the application. So the question is, how do we know that we are pushing the secrets to the right application? And it goes back to the same point that I mentioned earlier. How the hacker works, how hacker abuses the system. If they manage to get the credentials, to abuse credentials, they will be able to create a new pod definition and map secret to themselves, and nothing will help them. There is no authentication of application in this scenario. It just, if your YAML contains certain things and you manage to put them to etcd, that's it. You basically have every access that you need. And therefore, if I didn't mention before, but probably should have, Vault and even Azure KMS, they both have this integration with Kubernetes. So they both support push mode, and they proud that they protect the keys at rest in the Vault or in Azure KMS, but eventually they deliver those keys based on the record in the YAML file that sits in the same etcd. So if etcd is not protected, then there's no reason to do extra mile and protect the keys at rest somewhere else. The actual decision of delivering those keys to a specific application is based on the record that sits in the etcd. Okay, so just a little comparison. Let's see how we do on time. Actually, go very fast. A little comparison between the existing solutions. Okay, first of all, there are advantages to cloud KMS. Okay, the interoperability with the cloud services. For example, you can encrypt certain object in S3 and then use Amazon Athena service to do search over that object, and Amazon would automatically use the record in the KMS to decrypt him from also for you and for background cloud services. That's a good thing. Okay, that I don't want to underestimate it. Vault is obviously has nothing to do with this, and the Kubernetes secrets as well. In terms of multi-cloud, obviously cloud KMSs don't really play ball with each other, so there is no interoperability, and Vault can be deployed in any cloud, so this is an advantage. Kubernetes secrets natively cannot work on multiple clouds. You can do your own homework, your own configuration, and make sure that multiple clusters have the same secrets, but you will not get it from the mechanism itself. The secrets at rest are protected in Cloud KMS and the Vault, as we said. Let's consider them not protected in Kubernetes secrets, but I don't think this is really a big problem, especially when it comes to a cloud distribution of Kubernetes like EKS, AKS, or JK. How the identifier, the key requester is identified. Okay, in Cloud KMS we said it's token or KMS token or IAM token. In Vault it's a token, Vault token, and in Kubernetes secrets it's basically the record in the YAML file which sits in it's in that database. REST API is supported by all except Kubernetes. KMIP is only supported by Vault or others. By the way, Vault is a code name. Okay, don't get me wrong. Okay, there are others who support similar features like Vault. So I've looked at this as a category rather than specific implementation. A push mode is most popular. It came basically from Kubernetes secrets and then was picked up by Vault. I believe that Azure also have their own implementation, which I think they have done this with Hashicorp. At least 2 years ago at the KubeCon, they have presented together how they're going to implement the push mode and keep the secrets in their respective KMSs. But pay attention, none of them helps you when it comes to infrastructure as a code. None of them helps you to protect secrets in the YAML files, Helm files, script files that are sitting in Git, etc. So basically, you need to have probably more than one solution. We'll mention this in a second. So, a few words about how ARMO would help, or how ARMO would deal with these problems. First of all, a reminder, the secret lifecycle, okay, as I said before, when you create the secret, you need to back it up, you need to use it in the scripts, even before you load it to a key management system or Kubernetes in this case, they're all remained in clear. You need to build your own additional security solution. It's not the KMS phase yet. So if you back it up, you need to have security for backup. If you back up the scripts, you need to have security for backup scripts, etc. Once you load them to Kubernetes, they sit in etcd. As we said before, they sit in the clear. Okay, I'll let you judge how big of a problem that is. Okay, but once they basically move to a file, when they pushed to a workload, that file is also clear. And here, I believe the problem is pretty big, because most of the intrusions, most of the attacks that we see in the system, they're coming from injected software, abused software, and then any software can basically read that file and use that secret. So application will just simply read the file. How Kubernetes secrets would work with ARMO. Okay, first of all, the first thing ARMO will do is basically take the secret that was just created and encrypt it. From that moment on, you can put it anywhere. You can leave it on a bench in a park, because the moment it's encrypted, it's completely not dangerous. And it sits inside etcd encrypted. etcd keeps secrets under base 64 to avoid problems with dealing with binary data. So if you encrypt anything, it becomes binary data, and then you base 64 it, so it can sit there. Nobody will notice. It's completely garbage in, garbage out for the implementation for the Kubernetes. Kubernetes will then take it, and based on the name of the workload, just like Kubernetes Secrets does without ARMO, will push it as a file to the pod. However, in this case, the file has secrets that are encrypted. So even though they sit in the file, if somebody may have either overprivileged or stolen credentials, they will be able to ask Kubernetes to map this secret to them. And they will receive a file, but the secrets in the file will remain encrypted, which means that we're still not under attack. We still not have anything dangerous in our system. Now let's see what happens inside. Let's look inside, basically under the hood of what happens inside, because obviously application cannot deal with encrypted secrets. ARMO will automatically attach ARMO Guard, which is a micro agent. That first thing it does is basically creates a DNA or a cryptographic identity for a specific application. Application runs in a pod. Pod may run multiple containers. Containers may run multiple executables. The resolution goes to the level of a single process. You can enable the entire container or the entire pod to access that secret, but that's not a virtue. The virtue is how to enable it for a specific process that you want to give the secret to. Because if you have a bash running in the container and that bash can just copy a file and send it somewhere else, that would not be a great security capability. So ARMO will create a cryptographic identity of the process, which includes several things. First of all of the executables, all of the shared libraries, all the scripts, configuration files, environment variables, command line parameters, etc. All of them will be cryptographically signed and verified throughout the entire life cycle of the application process. So we can know at any moment in time what application is running. And again, it's not just done at the startup of the application, it's done throughout the entire application lifecycle. But the keys are sit in the file, they're still encrypted. So when application asks to read the file, what ARMO would do is basically the key would pass through the ARMO Guard agent. And once the application identity has been established, so we know exactly what application we're talking to, we know exactly this application is healthy and authorized to get the keys, the ARMO Guard will decrypt those keys on the fly, and it will become a part of the application process in memory. They will never be stored anywhere outside. When they are stored, they remain encrypted. But when they are inside application process memory, they will be opened. And the good news is that ARMO Guard will keep watching that application from the security standpoint, making sure that its identity didn't change. There's no post-deployment SO injection, or there's no post-deployment remote command execution that could actually alter either application code or application configuration data that may potentially disclose or abuse those keys. And this brings me back to the authentication. If you remember when we said at the beginning, the authentication has to be based on something that you know, something that you have, which has clear problem in the cloud environment, but it also can be based on something that you are. And this is exactly what ARMO Guard brings to the picture. We actually built the algorithm allowing us to authenticate application DNA, application code DNA, if you wish, that is allowing our system to know which application we are dealing with. However, there's one small thing I didn't mention here. I said the keys are encrypted, and you would probably want to ask me, okay, encrypted with what? You still need to decrypt them, so you need to get the key. Somehow you need to get the key to decrypt the application keys. Indeed, and this is the same problem of, as we discussed before, the problem of secret zero. This problem is not yet solved here. But what ARMO does is authenticates the application based on its DNA towards the backend system of our solution. And once that authentication is done, and this is the real authentication now, because we know the DNA of that code, we know exactly who we talk to. Nobody can copy that. If you copy that whole thing, you will be just running another instance of the same application that will do you no harm. So the mechanism which is able to sign and verify the application in the runtime is our authentication mechanism, with which we go to the backend system and get the key to decrypt the application keys. And this is how we basically close the loop. Now, you can see that the keys are basically protected all the way. From the moment they are created and encrypted immediately, you can put them anywhere. They are not dangerous. You can put them in the scripts, you can put them in the configuration files or YAML files or Helm files. It doesn't matter. You can keep them in Git if you want. When they load it to Kubernetes, they're still encrypted. When you define the access permissions, you can do it either with ARMO mechanism, which will be based on the DNA of that application, or you can do it with Kubernetes mechanism, and ARMO will pull that authorization at the moment when you're still in your safe environment and say, okay, now I know you've enabled this particular pod to access the keys. I can see inside, I know what application, what process in the pod has actually accessed that key in the staging, and I will give that process the permissions to access that key. However, only in the runtime, when application reads the file, it gets verified. And if it's healthy, if it's not compromised, and if it's authorized, then the file will be decrypted, the key will be decrypted and delivered to the memory of that application. So we now have a complete end-to-end security solution which provides complete encryption and authentication, delivering the keys from the storage to the application at the time of execution and keeping them safely there, because ARMO Guard will watch the application while the application uses the keys. That would be it for today. I think I was a little bit faster than I expected, but if we have some questions, I'll be happy to answer them.
All right, great, Leonid. You know, the first thing that kind of jumps out to me is it's amazing that they call Kubernetes secrets secret when they're not secret, right? I mean, it's kind of and you really need something like ARMO Guard to make them secure. So that's a really curious terminology, and it kind of gets back to what you said about doesn't make a difference what you call it, right? So I'm dating myself. When I started in the crypto world, it was cryptographic variables, and then they became keys, but they didn't change what they were doing. So that's you know, the terminology they have is kind of almost deceptive, right? What?
Well, I thought so too at the beginning, and as I said, okay, I was really curious about why they call them secrets if they are not secrets, and the answer I've received, and I think I actually respect this answer. Okay, really, there's the security side and there's a functionality side, and if Kubernetes designers decided to give you a separate way to define a permission, different level of permission for object access, I think it's a good thing. Okay, and they have done, you know, in the perimeter of what they could have done. I think it's a very good solution for them. However, we are not the only ones who say that Kubernetes secrets need improvement. Okay, the integration of Hashicorp with Kubernetes secrets and Microsoft Azure KMS with Kubernetes secrets actually says the same. We just take different approaches to doing that. And I think the biggest difference between what ARMO is doing and what others are doing is we are not involving application in anything related to that operation. Application thinks that it uses Kubernetes secrets as they are on their own, without any changes to application, without any changes to Kubernetes, and everything happens kind of under the hood.
Okay, all right. So we got a few questions here to show up, and it was kind of interesting. You talked about the methods, Cloud KMS, Vault, and the Kubernetes secrets. Is there a best method? If someone's picking those, or how would you go about assessing those and then layering on ARMO on top of them?
Well, leaving ARMO aside for a moment, okay, we can't say the whole world is ARMO. It's a good solution, but it's not the only game in town. So I think that between Kubernetes Secrets, Cloud KMS, and Vault, I would personally go with Kubernetes Secrets. I think that cloud vendors are kind of bluffing that they don't guarantee that etcd is well protected. Okay, I think the biggest problem, really, security problem that is not solved in any of them, is the authentication between application and the key management system. This is where most of the issues, most of the potential break-ins will happen. And from that standpoint, all three are completely identical. So I would rather pick one that is convenient to use.
Okay. All right. Here's a question that more technical, but I think it's one that you probably can deal with. So we got a question about that they use OpenSSL, and OpenSSL requires that keys be stored on a disk in files. But if you're storing in memory, how would you work the applications that use OpenSSL libraries or other applications, web servers, that are configured to read secrets out of files, not out of memory?
Well, first of all, there are many applications that are configured to read secrets out of files, not just OpenSSL, really many of them. They take it from config files, they take it from config maps, and Kubernetes secrets is a nice contemporary way of saying this, but I think it's not covers even 5% of the software that exists on the market. Still uses the legacy config files and data files. So what I would do is I would encrypt those files with something that I would put in the key management system, and then decrypt them when appropriate key management system delivers me the key. Again, you can choose KMS, you can choose Vault, you can choose Kubernetes Secrets, you can choose ARMO. That's another dimension of your decision-making process. But as far as a relationship between your SSL application and the file in which the private key is, I would encrypt that file and use a KMS to deliver the key to decrypt it.
Okay, great. So there's a question from Andreas about, you're talking about ARMO, but until they go and implement that, are there any other recommendations that they could handle immediately, such as shell variables or files to protect secrets?
Well, it's a very interesting question. First of all, yes, obviously there is always something that you can do. Okay, and you can go all the way back and look at your entire secret management architecture, which is a long way. But I think the most important action you can do today without changing what you have is to check for excessive permissions, to make sure that your secrets, wherever they are, they're mapped to those that are supposed to get them. Because misconfiguration and excessive privileges is really a big problem. Even before you start, protecting yourself from really targeted attacks and software intrusion attacks, which will happen, and you will have to do it. But today, the first thing, the lowest hanging fruit for you, is to go and make sure that you are not overprivileged and you're not you're not too wide open in the sense that somebody can access your secrets. And there's different ways of doing it. If you use cloud KMS with identity and access management, you probably have all your nodes enabled to get any secret, because you not always know where your workload is going to start. Okay, these are the places to look.
Yeah, so it really kind of, when you talk about permissions, it really goes back to need to know, right? I mean, permissions is just another way for saying someone needs to know this, and if they don't, they shouldn't have access to it. Yeah,
absolutely. And of course, the need to know, it doesn't mean that it doesn't have to be protected because it needs to know. You need to know, so you get it, but you still need to know how to protect it.
right. So, there's many stages you talked about. Excuse me. And so, is there any specific stage that you should start to care about your secrets, build, deploy, or does it? Is there one more important than the other, or how would you deal with that?
Well, from my experience, the attackers will always go for the weakest link. So we should not really try and improve one part while leaving the other one wide open. Okay, the entire life cycle of a secret, and this was primary reason why I decided to mention, is showing whether your secret, from the moment it's born to the moment it's consumed, you have to figure out what to do in every single step. How do you back them up? How do you protect them in the backup? How you put them in the script? How you put them in the key management system? Who can decide, or who can define the permission to access them, etc., etc. All of those stages are important. It doesn't necessarily mean that you have to one day finish all of them. It's probably impossible, but you do have to figure out what is the most kind of probable way for a potential bad actor to access your system, and start from there. I would recommend to go and look at the rules or maybe processes that you use to dedicate secrets to the applications, and who can access to them, who can change that kind of these rules, etc., and figure out, first of all, in terms of operations, how safe you are. And technology always takes longer than operations in this case.
All right, got time for one last question, and just going to throw it out there, since there's probably a lot of Kubernetes professionals, developers, security people here. So you got a little forum. So what would you tell them to do? What would some word of wisdom to help them maintain their security and to keep working to improve their environment?
Well, probably there is no one word answer. There's people who are professionals in Kubernetes. They may know these things much better than I do. So I think that the most important thing I would suggest to do is to make sure that there are no multiple systems involved. The problems most likely happens, between the chairs, and the cracks between the chairs, rather than on the chairs themselves. Each product takes care of its own, but if you have a chain where one product is responsible for secrets at rest, and another product is responsible for access rights, and another product is responsible for monitoring, I think that creates a nightmare that nobody can keep up with. So I think that Kubernetes is a unique opportunity. Kubernetes is a new thing, relatively new thing. Some people may disagree because they use it for a while, but still, in terms of market penetration, Kubernetes is the opportunity to align those technologies, to make sure that you don't have too many. I'm not saying have one, okay? That's it's extreme. But having tens like CISOs used to have in the past, I think that's too much. And I would start from reducing the number of moving parts in the architecture, and then, of course, evaluating the parts that I still have, and figure out if I can improve them and improve the connection between them.
All right, great. So we're pretty much near the end of today. So if you'd like more information about ARMO and the solution. You can find them at armosec.io. And Leonid, do you know if there's anything about the secret zero on the website? Because I have to say that is really the interesting problem, right? And
well, I must say that ARMO does much more things than just secret management. Okay, we build a solution for overall security of Kubernetes and security in Kubernetes. We build a complete zero trust platform. So if you look at our website, which by the way, I think we have a new look starting from today. If Jonathan is here, you can either agree or disagree on this. I think we've started a new website now, and we have a lot of information in there. And contact us if you need more information. But the key management is really a fundamental aspect that we wanted to talk about today.
Yes, and I'm sure you and I could talk for hours on these subjects, given my background too. So, but now it's time for me to announce the winners for the 4 $25 Amazon gift cards. And so those selectees are William E., Ada A., or Ida, Alex F., and Sean M. So you four will receive an email, and the email will be sent to the address that you registered for this webinar, and it will explain how you can receive your gift. And so please don't forget to check your spam folder if you don't receive it soon. So again, I want to thank you, Leonid, our sponsor, ARMO, and to you, our audience, for taking an hour out of your day to spend with us. So until next time, we'll see you later.
Thank you, everybody, and congratulations to lucky winners.